All Procedural, hi to you, and today's topic is what shaders are. This is a theoretical video that will serve as a good basis for future practical exploration of shaders in different software. There are more practical videos that are coming your way. We'll cover different shaders types in Unity and Unreal, and even talk about shaders in Blender. But today, it's purely theoretical. In a previous video, I've shown you several usages of shaders. If you haven't seen that, go and check it out, because why learn what shaders are if you don't know what they can do? Long story short, shaders can animate geometry, they can affect the output colors, and are also the key component of post-processing. Seeing all of that, you might think, that's a lot. Is that really one tool? And yeah, it is. While usages are very diverse, the core is extremely simple. Let's look at what you have to deal with. You have your input. All the data from your input goes into the vertex shader, after which it goes to the fragment shader, and finally you have your output. I could say it's a lot more complicated than that. I mean, there are geometry shaders, compute shaders, but 99% of the time this is all you'll need to know. Also, if you don't know what a fragment is, just think about it as a pixel. There are enough similarities and misunderstanding around it that it becomes an almost accurate representation. But say fragment, be smart. So let's dissect this simplified scheme and see where it takes us. Input. We'll delve deep into input in a later video. So for now, let's just say it includes mesh, which are vertices, normals, UVs, vertex color, textures, and material parameters. There's a lot more you can jam in there, but we're doing a friendly introduction before going in deeper. Wait, that came out wrong. Vertex shader. So, what does the vertex shader do? Basically, two things. It moves vertices into final positions, and it also defines data for interpolation and future use in a fragment shader. It is executed once per each vertex of the mesh. Just in case, 3D model, in other words mesh, consists of polygons. Each polygon is defined by several points, that is, vertices. Each vertex is, well, the actual container of most mesh data. Position, normal, UV, it is all stored in here. In fact, other than the vertices, mesh only contains a pivot point and a list of vertex indices to form triangles. I hope that was confusing enough, so we can continue. Let's go back to what does the vertex shader do. Vertex shader can change position of any vertex. This can be super useful for lots of different things, like animating wind or grass, ocean, fish, bloating things up, which could be useful for a toon shader or a snow shader, deforming things, trails, or damage. In fact, there's so much stuff that you can do with this that basically your imagination is the limit. But the technique is simple enough. You have position, which is a vector 3, and then you add some other vectors 3 to it. For example, you add normal to it, and then suddenly mesh bloats. This step is extremely important, as this defines what fragments will have in the fragment shader. Let me illustrate. Any fragment that has a part of the triangle is a fragment you have and can output something into. There will be no fragments outside of geometry. This is extremely important. You cannot draw anything outside of the geometry that you have after this step. Vertex shader also prepares data for future use in fragment shader. To understand what happens, you first have to know this. When it comes to rendering, geometry always consists of triangles.
But John, you're lying. Look, I have quads and multi-sided polygons. See?
Chillax. All still converted to triangles for rendering. In fact, here, I'll prove it. Here I have a single quad. When I start to change UVs, you can see them weirdly warping. The more the shape of UVs differs from the geometry shape, the bigger is the warp. The extreme case visually forms two distinct triangles. That's because they are two triangles. Look, if I divide the quad this way, the result visually stays the same. But if I do it the other way, see? Pro tip: triangulation may differ between software, so for consistent and expected results across software, it's good practice to export and use triangulated meshes. But let's get back to our triangles. Each triangle consists of 3 points. These 3 points are used to generate all the fragments needed to render the triangle. And since these fragments are located between vertices, the GPU blends the data from all the 3 vertices. This blend is always linear across the triangle, and never uses information from vertices or fragments on more than one triangle at a time. The computer graphics term for this blending process is fragment interpolation. So all the data the VERTEX shader outputs gets interpolated for future use in the fragment shader. And that gets us here, the fragment shader. Since we know all of the inputs so far, we can skip this segment entirely, because this does one thing only: decides what the final output is. How it does that is entirely up to you and your imagination. What isn't is the final output. And what is the final output? The values that are written to the back buffer on top of the existing ones. We'll cover back buffer and rendering in another video, so for now just think about it this way. Back buffer will be your screen in the next frame. Every object is rendered there one after another. And when the entire process is done, you have your final image that is sent to the screen. And now let's get back to the final output. The key output is color. It is almost always a part of the equation. It's important to note here how the color impacts what you see in the final image. You see, the color rendered is mixed with whatever color is already in the back buffer. The rules of such blending are called the blend mode. If you ever worked in Photoshop or another 2D layer software, you'll feel at home here. Imagine you have a blue quad rendering on top of a green background. Here are 3 most common blend modes with their respective blending formulas and the output results. You have your apex, which just renders it on top, disregarding anything behind it. You have your transparent. The lower the alpha of the pixel, the less the rendered color will matter. And you have your additive, which sums up the color values and gives you your result. You also can output STENCIL, which is just an arbitrary value from 0 to 255. Based on the STENCIL value, you can discard rendered fragments entirely. It is mainly used to mask things rendered after it. One key example of STENCIL usage is a tutorial fade, when you have a semi-transparent dark color covering the entire screen, but not a certain area inside of it. To highlight a button. One of the simplest ways you can do that is by using 2 quads. The small one will render only STENCIL value, for example 99, while the big one renders after and only if the STENCIL value in the back buffer does not equal 99. Finally, you can output depth. Most of the time, as long as you're rendering opaque, depth is just there, so we'll ignore this entirely. That's it. Now you know the basics of shaders. Congratulations! I hope you found that useful. For better knowledge retention, let's quickly recap what we've learned today. Shaders are easy. Vertex shader. Move points around. Pass the data to the fragment shader. Key point. You don't get fragments where you don't have geometry. Fragment shader. Output color is the key output and what you should focus on. Key point. learn your blend modes. They decide the destiny of color rendered before and color currently rendering. Want to mask things? Use STENCIL. Finally, repeat after me. Shaders are easy. One more thing. Shaders might look different in different software, but trust me, they're all the same. In the upcoming videos, I intend to show you exactly that. We'll cover a much more practical thing. First, we'll go over all of the shader types in Unity 3D, which there are a lot of. Then we go over Unreal Engine, and finally, take a look at Blender. Subscribe and push the bell if you want to see that content. If you found this video useful, please leave a like. And I'll see you at the next All Procedural.